Good day, my name is Amir Khandani. I work in the E&C department of University of Waterloo. I'm going to share some research results on something that I have called media-based modulation. It's a modulation technique which is based on changing the RF environment in the propagation channel from the transmitter to the receiver by perturbing the environment close to the transmitter antenna and thereby embedding information in the channel state which can be detected at the receiver. The word media here refers to the transmission medium. So the concept is that the information is embedded in the channel state, in other words, in the transmission medium state. To explain the basic idea, the best way is to think about it in terms of smoked signaling, in the sense that the message is formed outside transmit antenna and the message is encoded into pseudo-random channel states. The channel states contain the information which is detected at the receiver and converted back into bits. And of course, a forward error correcting code operates over those bits that select the channel state. Here I have an example of an antenna that has two distinct beams of energy gains of 0.5 and 1.5, which averages to 1. This is all the way the assumption that the average gain is 1. The transmitter has to use one of the beams, and the transmitter does not know which beam has higher gain. The intention is to form a 4-point one-dimensional constellation at the receiver. Option 1, which corresponds to legacy systems, is based on the following: that we select one of the beams at random and use a 4-palm constellation with a minimum distance of 1. We may be lucky and select the beam with the higher gain, but there is 50% chance that we select the beam that has a lower gain. So we are spending an energy of 5 divided by 4, which is the energy of that 4-palm constellation at the transmitter, and we are receiving a constellation that with 50% chance has a d mean of 1 divided by root square 2. To continue with the example, here I have the same two beams antenna, and this time I use the concept of media-based modulation. This means I want to transmit 2 bits of information. I use 1 bit to select the antenna beam. I select, for example, the left beam as represents bit 0 and the right beam represents bit 1. And I do not know which of these two has a higher gain. And then, regardless of which beam has been selected, I modulate a BPSK constellation with a minimum distance of 1. It's easy to see that the overall constellation received at the destination will be a 4-palm constellation with a minimum distance of root square 2. In this case, we have spent an energy of 1 divided by 4 instead of 5 divided by 4, and the minimum distance, worst case minimum distance, which also is equal to the best case, has been increased to root square 2. So if we put these numbers together, we see that we have had 10 times energy saving. To further explain the idea, here I have one practical example of the method to embed the information in the channel state. This round shape green unit that you see has an omnidirectional antenna in the center. This is an antenna with a donut-shaped radiation pattern, and it is surrounded by 14 walls. Those walls act as an RF mirror. We can turn them on or off, and as a result they become either a reflector or transparent to RF signal. So they let the signal to go through or it reflects it back. This RF mirror on its own is a new contribution. It has not been known in the literature to the best of my knowledge. As you see here, because the image of a mirror in another mirror will be a new image, with 14 mirrors we are able to generate 2 to the power of 14 channel states corresponding to which mirror is reflecting or is transparent. And this 2 to the power of 14 channel states can be used to modulate up to 14 bits of data. Of course, some issues here need to be clarified, that we do not need to use all these 2 to the power of 14 states. We can select a subset of them, maybe the subset that has a better channel condition, which requires some feedback from the receiver to the transmitter, or we can select a subset or all of them to embed information in the form of media-based modulation, and then having another modulation, legacy modulation, modulating the signal that goes through the middle antenna. In particular, for this last case of having some information embedded in the legacy format of modulation in the signal that prior to transmission from the central antenna, is useful to make the constellation that is due to the media-based modulation symmetrical, in the sense that by changing introducing 1 bit of information in the eye by inverting its sign, and another independent information bit in the Q by changing its sign, we can make the constellation to have 2 more bits of information and also make it symmetrical with respect to the 4 quadrant. The rest of this talk is the situation that the entire modulation is medium based. We are essentially not using any feedback from the receiver to the transmitter, and consequently the arguments of the channel capacity will be on the outage capacity, because at the end of the day the transmitter does not know what is the channel state. The way this can work is that the transmitter at the beginning will go through the channel states one after the other and index them by 0 to 2 to the power of k minus 1. Receiver measures them and knows that they are happening with this particular consecutive order, and will know what constellation configuration at the receiver corresponds to the which bit pattern at the transmitter. So here I have an example for the antenna patterns corresponding to some of the switching patterns. As you see, the antenna patterns have some weird shape, but each of them, because the signal gets propagated through a rich scattering environment, will correspond into a constellation point at the receiver with the components I and Q independent of each other, and assuming Rayleigh fading, each component of the constellation, each constellation point will have Gaussian component with 0 mean and unit variance. This is the property of Rayleigh fading. So here I have the example of those antenna patterns used in a software for ray tracing to see what kind of constellation point we'll get at the receiver. We have tried this on 2 model. One is for indoor, which is a residential home with dry walls, and the other one is the model for outdoor, which is part of the downtown in Ottawa. So here are the example of the constellations that we receive corresponding to the indoor and outdoor. As you see, the points are randomly distributed in the I and Q coordinate system. These points have IID Gaussian distribution for their components, and the mean of that Gaussian is 0, the variance is 1. As I mentioned before, and I will later show an example, these constellations can be symmetrized. We can introduce symmetry in them by modulating another bit of the sign of I and one other bit to change the sign of the Q. Consequently, we get four-way symmetry in the 4 quadrant. Here is the example of another constellation which has been converted into a symmetrical constellation by modulating another bit of information into the sign of I and an independent bit into the sign of Q. So you see the shape of the constellation is not very far from the uniform constellations that usually are used in conventional legacy modulation systems. And as we will see later, shown to you through some theoretical arguments, the capacity of this channel with IID Gaussian distribution for the coordinates of the constellation will approach the capacity of a Gaussian channel. So before getting into the main body of the talk, here I have some remarks. First, that assuming a rich scattering environment outside the antenna, the slightest perturbation in the environment close to the transmit antenna causes independent outcomes at the receiver. And also, in the literature on RF beamforming, there is something called parasitic beamforming, in which the antenna beamforming is performed by changing the environment outside the antenna through some parasitic elements. However, in antenna beamforming, the idea is to focus the energy at a particular direction and maximize the signal to noise ratio. The intention is not to embed information, and the intention is not to essentially have additivity of information over receive antennas, as we will discuss later, and so on and so forth. So in the previous slide, I mentioned that the assumption of rich scattering outside the transmit antenna results in independent realization of IID Gaussian component for the constellation point corresponding to each channel state. And this assumption is fundamental in our follow-up discussions. The question may come up that what happens if we have line of sight? So here I have example of another constellation realization in which the same antenna that I introduced before has been switched, but the transmission is line of sight. There is no reflection from the environment. And as you see, the propagations around the transmitter, which are the reflections of signals in those on or off mirrors, will create enough richness in the channel that effectively you get the same distribution of the constellation points. To continue the discussion, here I have a slide that is explains the benefits of media-based modulation versus what we have known in legacy systems, which I am calling source-based modulation. As mentioned earlier, the main idea is that the information is embedded in the variation of the RF channel external to the antenna. The assumption is that the transmitter doesn't know the channel state, which channel states corresponds to what configuration at the receiver, and blindly embeds the information by selecting those channel states, and the receiver knows what bit configuration corresponds to each of the received constellation points, which each constellation point corresponds to one of those channel states. Now, to go through the benefits, let's first assume that we have one single transmit antenna of the form that I mentioned with RF mirrors embedding the information in the patterns of the antenna, and I use multiple receive antennas at the destination. The important point is that the receive antennas will receive an independent realization of the constellation point over each of the antennas. So if I have, for example, 4 receive antennas corresponding to each bit pattern at the transmitter, I will have 8 IID components with Gaussian distribution at the receiver corresponding to I and Q of those 4 antennas. And the important point is that the distribution of the constellation points will be IID Gaussian. The fact that they are independent of each other brings the property that the information received over those separated receive antennas will add together. So this is one major difference with legacy SIMO systems, that in SIMO system the signal received at the destination will span always a single dimension, and the best we can do is to gather the energy through maximum ratio combining at the receiver, which will result in some energy saving but doesn't change the rate in this manner that we have a linear increase in the rate as a function of the number of receive antennas. So I am still at the first bullet about the additivity of information over multiple receive antennas. As I said, we use a single transmit antenna and we have an linear increase in the received information, in the mutual information as a function of the number of receive antennas. And if we compare a 1 by k media based system, 1 transmit antenna and k receive antenna, we have another benefit with respect to a k by k system. We have indeed 2 benefits, other benefits. The first one is that in a media based modulation, the noise over the receive antennas will be independent. However, in a k by k MIMO system, because of the non-orthogonality of the channel metrics, the noises will not be independent. Or if we want to look at the noises to be independent, the signal received will have essentially will not be on an orthogonal basis, and consequently we will have degradation in the performance. However, in a media based system, the noise at the receiver is independent and the information over the receive antennas add. Another benefit, I'm now at the second bullet, another major benefit which corresponds to both single transmit, single receive antenna systems or single transmit, multiple receive antennas, is that in media based we have an inherent diversity over a static channel, which I am calling constellation diversity. Because in a system, if you recall the example I had of those 2 beams, antenna with the 2 distinct beams, which selecting the beam with the lower gain could result in an outage event with probability 50%. When we randomized it, we saw that the outage essentially disappeared. We always had a constellation with 4 points, and the good and the bad were channel conditions which correspond to beams of lower and higher gain, contributed to building a single unified constellation at the receiver. So the concept of diversity and outage essentially changes into a whole new paradigm altogether. So the point is that the diversity is built into the constellation structure. Constellation points may have a low energy, which corresponds to channel conditions of low gain, or may have a high energy corresponding to the channel configuration of a higher gain, but of course, in any constellation with several points, a multi-level constellation, multiple point constellation, we always have points that are closer to the origin and points that are further away. So here, having channel conditions that have low gain and contribute to the points that are close to the origin, it's not really a bad phenomenon, at least not as bad as it was in the case of a source-based modulation with a static channel. Now coming to the second sub-bullet, essentially this means that in a 1/k media-based modulation, unlike MIMO, unlike a k/k MIMO, to achieve or to increase diversity does not require sacrificing the rate. So it's well known that when you have a MIMO system, you can trade off diversity versus multiplexing gain. So increasing the diversity means that you are compromising in the achieved rate or order of the increase of the rate with bandwidth. However, here this is not the case. The diversity is automatically realized. And coming to the third sub-bullet, as we will see through some math, this feature essentially converts the static Rayleigh fading channel into an AWGN with the same average receive energy. So essentially means if you have a static Rayleigh fading with the statistical average of the channel gain equal to 1, you get, and the noise of variance sigma square, you get an AWGN channel with variance sigma square. And if you have K receive antenna, you get K of those channels parallel. Although later on I will come to this point, but I would like to clarify here that when we have K parallel channels, we need to spend K units of energy at their input. However, in a media-based modulation, we transmit a single unit of energy over a single transmit antenna, and we receive K units of energy. So this feature of energy harvesting is another benefit that we get compared to having purely 4 parallel channels. So here I am getting into the mathematical model, and I will give a brief overview of mathematical derivation of the method to do it, which is also, I have not seen any similar treatment in the literature. Because of the special features of this problem, I had to come up with some new mathematical approaches to compute the capacity. So here I have essentially the red part at the beginning of the channel is where the carrier changes, where the carrier enters, and the data changes the state of that red part. The net effect is that the information which is shown by the parameter m is uniquely and one-to-one mapped to a channel state, which is shown by vector hm. This is the vector of IID Gaussian components that I will receive over the receive antennas. So if I have K receive antennas, the vector H will be of size 2 times K, corresponding to 1I and 1Q for each of the receive antennas. And as you see, the expected value of the norm of that vector is 1, corresponding to the normalization of the fading. The channel is additive Gaussian noise, so I have the vector Z as the noise added. If my channel, if my constellation has K receive antenna, this vector Z will have 2K IID Gaussian components with variance sigma square. So the output to the channel will be a vector Y, which is H plus Z. H is blindly selected by the transmitter by selecting according to the value of M, and vector Y is received at the destination, and from vector Y the receiver intends to extract the information bit pattern M. Because the channel is additive noise, we can write the expressions for the mutual information, and the first line of the mathematical expression follows that we have the entropy of the output minus the entropy of the noise. Now, one point that I would like to clarify here, the fact that we end up with a constellation with IID Gaussian component essentially aligns with the requirement of random coding over an additive wide Gaussian noise channel. So it's a desirable feature. And as we will see, this feature eventually asymptotically converts the channel into an AWGN channel. However, there is a difference between this method and the conventional random coding as we know it. In random coding, the constellations are selected with IID Gaussian components, but independent from transmission to transmission. Here we have one realization of the constellation with IID Gaussian components. However, unlike random coding, we continue using the same constellation throughout the transmission. This may result in an outage event and will have some loss with respect to the actual random coding in which the constellations are selected independently. The mathematical derivations that will follow show that, first of all, provide bounds on the differences between this capacity of such one realization of this constellation, average loss of the realization of media based versus what we would get with IID Gaussian component corresponding to random coding. As I mentioned before, we have a constellation corresponding to those realizations of vector HM that is fixed throughout the transmission but has IID Gaussian components. So the constellation with M point is selected once with IID Gaussian components and used throughout the transmission. To measure the degradation of this type of modulation with respect to what traditional random coding does, in which the constellations are selected independent of each other from transmission to transmission, and consequently the distribution at the channel input will be Gaussian. To measure this degradation, I am introducing some form of quantization with that vector NQ. The vector NQ is a vector, please refer to the article for details, that will convert HM into vector Y, and vector Y has a Gaussian distribution. The way that this vector is derived, its dependencies, and the way that the expressions are formed, please see the details in the article. At the end of the day, we will be able to write some expressions and bounds for the mutual information, and as you see here, I have expected value in the first expression. Second term, I have expected value over C. This expected value over C is the expected value over different realization of the constellation. So my intention is to say, let's select one constellation with M point 2k dimensions, k is the number of receive antennas, with IID Gaussian components, apply a random coding with uniform distribution, selecting this constellation points to the resulting channel, compute the capacity. Select another realization of this constellation with the same feature, compute the capacity. And do this many times and compute the expected value over the realization of such constellation, which is in that term expected value over C. The first line is essentially the expression we get. The point is, we will show that the article will show is that this expected value, when the M increases, this expected value tends to the noise entropy in an ordinary AWGN channel. And consequently, our capacity will tend to the capacity, the expected value of the capacity will tend to the capacity achieved through random coding over an AWGN channel, which is known to be the maximum, and consequently when the average meets this upper bound, then with probability 1 different realization achieve the capacity of the underlying 1 times 2K Gaussian channel. But please, I repeat again, it's not 2K parallel channels, because 2K parallel channels will require 2K units of energy at the transmitter. Here we transmit 1 unit over energy over I, 1 unit over Q, or 1 unit of energy over a complex coordinate system at the transmitter, and we receive independent units of energy with independent information over receive antenna. So we send 1 unit of energy and we have a factor of energy harvesting of K. So to come to the last line, essentially this sigma square of NQ condition on H is the variance of the quantization noise, and we show that this variance is less than the expression you see at the end, and this goes to 0. Now I use the word upper bound. I would like to clarify here that these expressions that we have for the achievable rate to a good part of the derivations are indeed a lower bound on the achieved capacity, but at some point it will be approximations when I want to compute the essentially variance of the quantization noise. But at the end of the day, the conclusion we would like to draw is that the variance of this additional noise, which is sigma 2 of NQ condition on H, tends to 0. Consequently, I will get the same capacity that in random coding over an AWGN channel would give. So here I have a continuation of the same expressions. Don't want to get into the details of this, but at the end of the day, the sigma 2 variance of the quantization noise NQ condition on H, which essentially measures the degradation of the average rate averaged over different realization of the constellation of media-based modulation with respect to an actual AWGN channel. This variance tends to 0 with 1 over L to the power of 2 divided by K. L is the number of constellation points and K is the number of receive antennas. Now here we come to the main conclusion of the article, that if we have a slow Rayleigh fading channel, slow here means static. In other words, the channel does not change over one realization of the coding block, over one coded block. And the statistical average of the fading gain per receive antenna is 1. Then, using a single transmit and Q receive antennas over such a channel, the mutual information averaged over different realization of a constellation with L points approaches the capacity of 2 Q parallel AWGN channels, each with unit energy as L tends to infinity. So the Q is real dimension, K is complex dimension. K is the number of receive antennas, and Q is always equal to 2 times K. Now, as I mentioned this, in order to prove the main result, I have used some new techniques for essentially modeling the degradation in the capacity of a channel because of using a static constellation with IID Gaussian component, but it's static, doesn't change from transmission to transmission, which is unlike the traditional random coding, I have modeled this as an additive noise. And in the paper, you will see some expressions for this essentially quantization noise. To a good part of derivation are based on actual lower bound, and then at some point it will be approximations, but the approximation serves our purpose of showing that the capacity approaches the capacity of AWGN. Here in these curves, I have an example for the accuracy of those expressions that are in the article. So the blue curve here shows the simulation of a 256 point constellation with Q equal to 1, means that the single real dimension system is SISO. The blue curve, which is simulation of the actual average, is essentially based on generating a lot of different constellations with each with 256 points, with IID Gaussian distribution for each point, computing the capacity of that constellation over an AWGN channel and averaging those capacities. And then the two other curves, which are lower, corresponds to expressions that I have in the paper, which corresponds to, one is their complete derivation, and the other one which is based on some simplification. As you see, although I'm not claiming that this is a bound at the end of the day, but it's clearly for at least this example shows that we have all the way a bound. But the point is that when the gap between the expressions that I have with respect to the AWGN, the gap goes to 0, so it doesn't matter if it is a bound or it's not a bound. Here I have some numerical results showing the main benefit of media-based modulation, which is in inherent diversity in a single constellation. As you know, conventional modulation methods suffer from deep fades, resulting in outage event in slow fading channels. However, this problem essentially disappears in media-based modulation because good and bad channel realizations contribute to forming a single constellation, which is the constellation used for communication. Good channel condition means channel conditions with a higher gain, and bad refers to channel conditions with lower gain. So channel conditions with higher gain corresponds to constellation points further away from origin, and likewise channel conditions with low gain correspond to constellation points closer to the origin, which we need anyways. Like in any modulation, for example, a 256 QAM, we have some constellation points that are closer to the origin and some that are further away on different shells of energy. The curve that we see here corresponds, the x-axis is the signal to noise ratio, the y-axis is the mutual information. The blue curve corresponds to the mutual information of a 256 QAM with the transmit energy resulting in the signal to noise ratio shown on the x-axis. For the case of 256 QAM, the energy is the transmit energy, and which is also the receive energy. The 256 QAM is for over an AWGN channel, and the 256 QAM is used with equal probability, uniform probability for its points. So you see we have a curve that has a SNR of 0 dB, starts from 1 bits per 2 dimension and saturates at 8 bits per 2 dimension. Then I have the 10,000 random realization of a media-based modulation, meaning 10,000 different constellations, each with 256 points, and for each of those constellations, the components I and Q, or X and Y, of the constellation points are generated with IID Gaussian random number generators, and we have the same additive noise at the receiver, and we see that the corresponding 10,000 realization. For each of them, the mutual information is computed and are plotted. So as you see, for the 10,000 constellation points, for the 10,000 constellation realizations, we have a spread of different mutual information, and the x-axis for the case of the media-based modulation, which are those random constellations, corresponds to the receive SNR, because sometimes we may get a constellation for which the average energy is higher than 1, or the average energy may be lower than 1. Consequently, we get for different realization, we have different mutual informations and also different SNRs, receive SNR. So those vertical red lines, which look like vertical, they are the span of the mutual information of the 10,000 different realizations, which doesn't have too much of variation. So essentially, I have plotted them, the minimum mutual information, the maximum mutual information corresponding to, for example, 20 dB and 25 dB. So the point is that the mutual information has a span of about 0.2 dB between the worst to the best. For example, for the 20 dB, it can go up to a little bit more than 256 QAM. Majority of cases is less than 256 QAM, but it's never less than 0.2 dB below the 256 QAM. Now let's focus on one particular point. Similar behaviors are observed over all points before the knee of the curve. So let's look at the SNR of 15 dB. For SNR of 15 dB, for the case of 256 QAM, the transmitted SNR and the receive SNR will be the same, and we get something like 4.8 bits per 2 dimension when the 256 points are used with equal probability. However, though in the subplot we have a cloud of points, and those are, each point correspond to one realization of the 256 points random constellation, which has a different energy and a different mutual information. Usually constellations which have higher energy, receive energy, has also higher mutual information. So the important point is that for this 10,000 realization, this cloud extends from receive SNR of 14 to 16 dB and the mutual information of say 4.5 bits to 5.2 bits or 5.1 bits. The important point is that if we have a margin of about 1 dB or maybe less for this random signaling, we are sure that with high probability none of those 10,000 realization will be in outage. So this gives an idea that what kind of margin for the signal to noise ratio we need to avoid outage. This margin decreases and shrinks to 0 as the constellation size increases. Now let's look at the case of a static channel. For a static channel to have a probability of outage of 0.1, we need about 10 dB of over provisioning of transmit energy versus 1 dB that we had for media based. For probability of outage of 0.01, we need 20 dB. For probability of outage of 10 to the power of minus 3, we need 30 dB. While for the case of media based, for 10,000 realization, you see that if we have a provision of about 1 dB, we'll never get into none of those 10,000 realization get into the situation that the mutual information is less than 4.8, which is what we expect to have. Here I have another curve in which we will be looking at the average rate, meaning that the statistical average of the achievable rate averaged over different realization of the random constellation for a 256.2 dimensional media based modulation. So those black dots are the mutual information corresponding to 256 QAM. The dashed blue curve corresponds to generating a lot of different constellations randomly, computing the mutual information corresponding to each of them, and averaging. As you see, the average for the case of 15 SNR of 15 is almost indistinguishable from the mutual information corresponding to that 256 QAM, and for the case of 20 dB is only marginally lower. And then the other two curves, red one and the dashed black one, corresponds to the expressions that are in the article for the mathematical expressions that we have for the mutual information, which shows that the expressions have a good accuracy as compared to the actual. Now again, the number at bottom show that in order to have an outage of 0.1 or 0.01 or 0.001, we need a margin of 10, 20 or 30 dB for a static Rayleigh fading channel. Here I have another perspective on explaining the benefit of media-based modulation versus source-based. So on the top part, we have a MIMO, K by K MIMO. K is the number of antennas. Consequently, the space is 2K dimensional or K-dimensional complex. In the case of MIMO, energy is distributed equally between transmit antennas, and the receiver has independent noise, but the channel matrix H is not orthogonal. Consequently, what we get is either we have to look at it as a signal being expanded over a non-orthogonal basis, or the noise at the receiver being correlated. Although the noise is independent, but the two are equivalent to each other, that if you want to look at the signal as independent, the noise will be correlated. The lower one shows the media based. So we focus all the energy over a single transmit antenna. So instead of E divided by K, we have 1 unit of energy going through a single antenna. And here, over the K receive antenna, we have independent realization of the constellation, consequently information add. This additivity of information is proved in the article as byproduct of the derivations that we have, showing that variance of the additive noise goes to 0, because over there is for 1 transmit antenna and K receive antenna. Now, the point is that for the media based, the noise at the receiver is added and is independent, and the information also adds. Consequently, we have a benefit with respect to MIMO, that the noise at the receiver is independent. And as we will see in the next few slides, this results in some significant, sometimes significant gains for media based. Please let me also clarify one point, that here by the term energy harvesting in this presentation, I have been referring to the fact that, for example, in a MIMO system, when you send an energy of E divided by K over each transmit antenna, the energy received at each antenna will be K times increase, because it will receive energy from all transmit antennas. Consequently, the energy at the receiver will be E. So we have an energy harvesting by a factor of K. This is of course not energy harvesting, just net effect after including the effect of shadowing and propagation loss and so on. In the case of media based, we have a similar effect in the sense that now we put all the energy over a single transmit antenna, E, and the energy over each receive antenna will be E. If I want to have K parallel AWGN channel, however, we need to transmit K units of energy, or K times E, E units over each. This energy harvesting is a feature of both MIMO and media based, which is a benefit with respect to K parallel channels. However, the in the case of MIMO, the gain essentially, because the channel is non-orthogonal, we will see that we will have some degradation. But in the case of media-based, the channel also is equivalent to an orthogonal channel, so we have both energy harvesting and independence of the noise over receive antennas. So now let's look at the outcome of the fact that the channel matrix in a K by K MIMO is not orthogonal. As the channel is not orthogonal, in achieving the capacity, when the transmitter knows the channel, it's well established that we perform eigen beamforming, in the sense that we use the input eigenvalues of the channel matrix as the basis, and we do water filling over those coordinate corresponding to the individual eigenvalues of the channel matrix. The net outcome is that the MIMO channel, if the energy is low, is not a k-dimensional system, k-complex dimension. It starts at the lower part of that curve. The slope is the largest eigenvalue of the channel matrix. In other words, when the energy is low in K by K legacy MIMO, we focus in the water filling all the energy over a single dimension, which corresponds to the eigenvalue to the dimension with the largest eigenvalue. And for the case of a V-short matrix corresponding to a Rayleigh fading channel, it's known that the expected value of the largest eigenvalue is less than 4, increases with K, and this expected value essentially tends to be approaches 4 when K goes to infinity. So the expected value of slope is always less than 4. Gradually, as the energy increases, we reach to a point that we have the first breakpoint in that red curve. So we get into a situation that we have enough energy to occupy 2 dimensions in the water filling. So the slope from that breakpoint to the next breakpoint becomes this lambda 1 plus lambda 2, which is essentially the largest eigenvalue and the second largest eigenvalue. And gradually we occupy more and more dimension. Eventually we will reach to a situation that all the K dimensions are occupied, and at that point it's essentially when we reach to a slope of K for the legacy MIMO in increasing of energy rate versus energy. However, in a 1 by K media based, because the noise over the receive antennas is independent, noise components over the receive antennas are independent, this slope of K will start right from the SNR, very low SNR levels region, and at low SNR, which are typically where we operate, the gap between this blue and red curve can be significant. So our discussions so far have been based on a transmitter that blindly select one of the possible channel states to communicate certain bit pattern to the receiver. However, when we have a certain number of channel states, it's known that we can select a subset of them and use the subset for which the mutual information is larger for communication. This requires some feedback from receiver to the transmitter to agree on the subset, and the net outcome of it is that we will have a selection gain. For example, when the SNR is very low, it's to our best of benefits to use a constellation with only 2 points, and we select those 2 points to be the points that are essentially further away from the origin, and we do the sign change in the signing, changing the sign of I and Q to embed that other information. So essentially at very low SNR, we'll get a QPSK constellation with a very large norm. And that norm, if you have, let's say, X number of possibilities for the channel, it's known from the discussions on the multi-user diversity in networks that the gain scales in the selection. The selection gain scales with the log of n in energy, with the log of x, the number of possibilities. Now, with this preliminary arguments, here I have the concept of selection gain, which means that we select a subset of points which, subject to a uniform probability distribution on the point, maximize the mutual information. The curve that I have, the x-axis is the signal-to-noise ratio, and the y-axis is the mutual information. The red one is the blue one is the essentially curve corresponding to selecting the best constellation. So we generate a lot of constellation, we get which one has the highest mutual information for that particular SNR, and we plot the maximum. The red curve corresponds to the 16 PAM, which is 256 quant. So as it is seen up to some point, for example around 12 dB, selection, which results in that blue curve, can provide a constellation which has even a higher mutual information as compared to the regular 16 PAM with uniform probabilities. The red curve is based on a simple selection rule motivated by the previous slide, in which we saw that the slope of the rate at low SNR is determined by the maximum, by the norm of the constellation points of that QPSK that I mentioned, and consequently we can essentially, in that red curve, what we do, we select constellation points that have the highest energy and add them and decide how many is to our advantage to keep. So you see that the red curve does not deviate a lot from the blue one, which is the optimum. So essentially, if we would like to have selection gain and we have 256 possibilities and we would like to agree on 64 points to transmit 6 bits, if we select the 64 points that have highest energy, we are very likely to perform close to the best that we can do. And if we are at a relatively low SNR, this selection is something that can essentially become useful. So after discussing both the behavior of the effective dimensionality of a 1 by k MIMO, media based, versus a k by k MIMO, and also the selection gain, now we come to the point of comparing a media-based modulation versus a legacy system by looking at the slope of rate versus signal-to-noise ratio at SNR of 0 dB. For a legacy SISO, the slope is 1. For a legacy k by k MIMO, the slope is the maximum eigenvalue of a k by k Wishart matrix, for which the average value is upper limited by 4. And for a 1 by k media base, the average value starting from SNR of 0 is equal to k. The table here compares the actual realizations. For the k by k MIMO, the 1.75, for example, that we have for k equal to 2, and 2.45, 2.96, and eventually converging to infinity. So in the lower row, we have the media based, which starts with k and it is equal to k all the way. Now, as I mentioned before, if we want to also use the selection gain to further increase the slope, the best scenario is to select constellation point with maximum norm. So essentially, our selection gain will increase the slope based on the maximum norm, which scales with log L. And further detail of this is available in the article. Here I have some comparisons in terms of the ergodic capacity. The ergodic capacity for the case of legacy system, which here is shown by SBM, meaning source-based modulation, is the capacity corresponding to water filling over eigen vectors, and essentially it's an unfair comparison to media-based because it's essentially the best capacity that the legacy MIMO or SIMO system can achieve. However, the curves from left to right corresponds to the different number of receive antennas, 2, 4, and 8. The blue curve is the capacity of a 1 by K, single input, multiple output, media-based modulation, 1 by 2 SIMO MBM, 1 by 4 SIMO MBM in the middle curve, and 1 by 8 SIMO MBM in the right-hand side, curve on the right-hand side. The solid red curve is the curve that should be compared with this blue curve, which is the SIMO source-based modulation, legacy SIMO system. And the dash curve is the MIMO version of source-based modulation. So as it is seen, we have some decent improvement in energy saving versus K by K MIMO. So in all cases, the capacity of 1 by K SIMO MBM outperforms the K by K MIMO SBM. The reason is the orthogonality of the coordinate system that I mentioned earlier, and the gains with respect to a legacy system with comparable number of transmit and receive antenna is significantly higher. However, as I mentioned earlier, the benefit of essentially a media-based modulation is in the fact that the diversity is built in, and to achieve diversity we do not end up compromising the rate. So the comparisons in terms of the outage in terms of the ergodic capacity is rather unfair to the media based. In other words, for the legacy MIMO system, analysis between outage and ergodic capacity shows significant difference in terms of the comparative comparison between these two notions of capacity. However, for media-based modulation, these two quantities are essentially become the same as the constellation size increases. To continue with the numerical results, here I have some comparison in terms of the outage capacity comparing a legacy system shown here by the acronym SBM, standing for source-based modulation, versus a media-based modulation shown by the acronym MBM. The curves corresponds to the outage capacity for different probabilities of outage, and these curves, the first one on left top is for a SISO, single input, single output, then will be for 2 receive antenna, either with 1 or 2 transmit antennas, then will be for 4 receive antennas with either 1 or 4 transmit antennas, and finally for 8 receive antennas with 1 or 8 transmit antennas. And for the case of outage of the legacy system, we have the curves for different outage probabilities of 0.1, 0.01, and 0.001. As these curves show, there is significant gain for using the media-based modulation, which is due to that inherent essentially diversity that comes with the constellation, that does not require sacrificing the rate to achieve it. And it happens for the case of SISO or SIMO media-based modulation. This brings me to the end of my presentation. Thank you very, very much for listening. This work has been presented at ISIT 2013 and subsequent more mature version of it in ISIT 2014. Some people have helped me with the simulation in terms of both numerical simulations for different curves that I presented, and also for the RF ray tracing and to obtain those antenna patterns, and they have acknowledged them in the articles. If there are any questions, my email is here, khandani@uwaterloo.ca, and I will be very delighted to answer any possible questions or comments that you may have. Would be very much welcome and appreciated. Thank you and best wishes.